Hello students, welcome you all to next session regarding discussion of the module number 3. In that, the second part is the reaction turbines. In the previous part, we have studied regarding the impulse turbines, steam impulse turbines, where we have discussed regarding the blade efficiency for a single stage impulse turbine, blade efficiency for a multi-stage impulse turbine, and we have solved some of the problems using the graphical methods. In today's session, we'll be discussing regarding the reaction turbines, the analysis of reaction turbines. Then we'll be discussing the condition for maximum blade efficiency, then the reheat factors, and the some more other things. So if you have any doubts, you can send me an email to the email address which are visible on your screen, which I'm highlighting here. You can send me a WhatsApp to this mobile number which is being displayed, or you can subscribe to my YouTube channel where there are videos where I post my videos. You can write the comments there also. So now let us begin the today's session regarding the discussion of the reaction turbines. So initially, the reaction turbines are nothing but these are the turbines where the steam expansion takes place both in the fixed blades as well as in the moving blades. So here in these turbines, the steam goes on continuously expanding in both the blades, that is the fixed as well as in the moving blades also. Therefore, fixed as well as moving blades also, the steam expansion happens. As a result, here along with the impulse force, the reaction forces are also developed, which are responsible for the work development or the work transformation. The effect of continuous expansion in these moving blades, it is responsible for increasing the relative velocity of the outlet velocity triangle. So therefore, you can say that here in the reaction turbines, the relative velocity at the outlet, it is always greater than the relative velocity at the inlet. That is VR2 greater than VR1. Also, if you observe this combined velocity triangle in the picture, you can see here in this reaction turbines, we are having some of the features. That is, you can see here, this is the combined velocity triangle, and some of the features, if you observe here, alpha 2 angle, it is equal to the value of beta 1. That is, V2 is equal to VR1. Also, if you observe carefully, the angle of alpha 1, it is equal to beta 2. That is, V1 is equal to VR2. And if you observe carefully, even this point, that is VF2 and VF1, both are same, which means even the flow velocities are also same here. These are some of the features of the reaction turbines. Now, moving ahead. As I said, the degree of reaction for the reaction turbines, it is defined as the ratio of enthalpy drop which happens in the moving blades to the enthalpy drop which is going to happen for both the fixed blades as well as the moving blades together. So here, if you observe here in the picture carefully, as I said, the enthalpy drop we take initially for the moving blades, that is this one, delta HM, then to the ratio of the sum of both, that is the fixed blades and moving blades together, we take into consideration for our analysis. So in the picture you can see here delta HM is nothing but they are representing the moving blades, whereas delta HF is representing the fixed blades. So if we represent this on a Mollier chart or on HS chart, the representation in this fashion, here you can see the steam expands from P1 to P2 pressure. If there is an isentropic expansion, this is the nature of the curve, moving a straight line downwards. But due to the losses occurring, it shifts from a new curve which takes a form H1 to H2, H2 to H3. So the difference between H1 and H2, it is giving nothing but the enthalpy drop which is occurring in the fixed blades. Similarly, the enthalpy drop which is occurring between H2 and H3, it is the enthalpy drop which is occurring in the moving blades. These are the things. So as I said, the degree of reaction is a thing, but it is the ratio of the enthalpy drop which is occurring between the moving blades, that is delta HM divided by the ratio, the sum of both delta HM plus delta HF, including the enthalpy of fixed blades as well as the enthalpy of the moving blades. So here mathematically I can write this expression as R is equal to delta Hm by delta Hu, that is the sum of both the fixed and moving blades together, or I can write it individually in this form also. So therefore, this enthalpy drop in moving blades, that is delta Hm, we can write in the terms of velocity terms as Vr2 square minus Vr1 square by 2gc. Now, you can write this as in the form of for a particular stage, and always remember a stage means it is a combination of both fixed and moving blades together. So here now I am finding out the total enthalpy for a given stage, that is W is equal to delta Hf plus delta Hm, that is considering the fixed blade and moving blade together. So this is the thing what Euler's energy equation itself. So our Euler's energy equation I can write it as U into Vu1 plus Vu2 by G, or this is the thing but together it is the thing, it is representing delta Vu itself, that is the Euler's energy equation which I have studied previously. So the degree of reaction, I said the ratio of the moving blades enthalpy drop, that is this one, this is delta Hm, the sum of the ratio of the moving blades to the ratio of the sum of both the moving and fixed blades together, that is this particular part, that is nothing but we are including delta H naught, sum of both moving and fixed blades together. So now I can write this as in this form after simplification, that is this I can write it as Vr2 square minus Vr1 square 2gc, and on simplification I get it as in this form, that is U by gc, and on simplification it becomes Vr2 square minus Vr1 square by 2u into Vu1 plus Vu2, or taking from the analysis of a velocity triangle, that is the outer velocity triangle with respect to beta, that is this particular velocity triangle, that is GFB, this particular velocity triangle making an angle of beta. I can write sine beta 2 as opposite side Vf2 by Vr2. This or this I can relate in this form also, that is cosec 1 by cosec beta 2 is equal to Vf2 by Vr2, or it becomes Vr2 is equal to Vf2 cosec beta 2. This is for the outer velocity triangle. Similarly, with respect to the inner velocity triangle, that is DBC making an angle of beta 1, the same correlation I can write it as Vr1 is equal to Vf1 cosec beta 1. We name these equations as 2 and 3. Now moving ahead, for the inlet velocity triangle DBC, that is for the inlet velocity triangle DBC, I can write cot beta 1 as adjacent side of opposite side. So the value of my adjacent side is, it is nothing but Vu1 minus U divided by Vf1, or the same I can write it as Vu1 minus U is equal to Vf1 cot beta 1. Similarly, with respect to outer velocity triangle cot beta 2, I can write it as from here Vu2 plus U divided by Vf2, or it is nothing but I can write it as Vu2 plus U is equal to Vf2 cot beta 2. Now the next step what I will do here is I will sum these both together, these equations. So on summing both these together, you can see here we get Vu1 minus U plus Vu2 plus U is equal to Vf1 cot beta 1 plus Vf2 cot beta 2, or this I can write it as on simplification it becomes this form, that is minus U plus U gets cancelled, and we are remaining with these terms, that is Vf1 cot beta 1 plus Vf2 cot beta 2. We are remaining with equation number 4. Already we have derived the value of Vr1 and Vr2 in the equation number 2 and equation number 3. We have got here value V1 and V1 plus Vu2. So both these together I can substitute my in equation number 1 where I have written degree of reaction R. So what I will do the next step is I will substitute all these equations 2, 3, 4 in equation 1. We get it in this form. Students, please observe here. Already I have said previously that in the reaction turbines, the value of Vf2 and Vf1 both are same. So what I can take it as, I can take this value as Vf1 Vf2 is equal to Vf. And if I substitute with this simplification in this particular equation, you can see Vf is common on both sides. So automatically after simplification, I get it in this form. That is, flow velocity is constant. You can see here, and you can see here the cancellations can be done. Here it gets cancelled, here it gets cancelled. You are remaining with Vf by 2u cosec square beta 2 minus cosec square beta 1 by quad beta 1 plus quad beta 2. One more important students here, this trigonometric function, that is cosec square beta 2, I can write it as in this form, that is 1 plus cot square beta 2. Similarly, for cosec square beta 1, cosec square beta 1, I can write it as 1 plus cot square beta 1. With these substitutions, I will do it in the numerator part of the degree of reaction, and I can go for further simplification very easily. So further, as I said, we make this simplification 1 plus cot square beta 2 minus 1 minus 1 plus cot square beta 1. You can see in the numerator part, which you have done here. And now what I will do is I will open these brackets such that after opening the brackets, it is in this form. Here plus 1 minus 1 gets cancelled, and you are remaining with these terms cot square beta 2 minus cot square beta 1, which is nothing but of the form a square minus b square, which means you can write it as a plus b as well as a minus b. So now I write it in this form. You can see here these terms a plus b cot beta 2 plus cot beta 1, and this terms gets cancelled, and on simplification I get this term. So now degree of reaction, that is already, as I have told, that the degree of reaction for a reaction turbine, it is having 50% reaction force, which means the value of R, it is equal to 50%, or this is equal to 0.5, or this 0.5 can write it as 1 by 2. So I'll substitute the value of 1 by 2 here in the LHS part of this particular equation, where I can get this form. So you can see here, this 2 gets cancelled, and on simplification I get it as u is equal to Vf cot beta 2 minus cot beta 1. This is the analysis for the particular reaction turbine. Similarly, the next we need to find out is the condition for maximum efficiency of a reaction turbine, which is also known as Parsons turbine, or it is also known as blade efficiency also. Some textbooks has mentioned blade efficiency of Parsons turbine, in some textbooks has mentioned efficiency of reaction turbine. All are the same itself. Before we begin the conditions for this one, we need to make some assumptions. Assumptions are the degree of reaction is 50%. Both the moving blades and the fixed blades are symmetrical in nature. And another very important point and the important feature of the reaction turbine is the steam velocity of steam which is leaving the first stage will be the same as the velocity of steam entering the next stage, that is V2 is equal to V3, which means there are no frictional losses. Now this is the combined velocity triangles for a reaction turbine, and here our Euler's equation, that is work done per kg of steam, is written as U delta VU by GC. W is equal to U delta VU by GC. So considering the inlet velocity triangle, that is DAC, this velocity triangle I consider making an angle alpha 1 with the trigonometric function of cos alpha 1. So cos alpha 1 is equal to, you can see adjacent side is VU1 by V1. VU1 by hypotenuse is V1, or the same I can write it as V1 cos alpha 1. Similarly, if I make with the outer velocity triangle, that is GFA, that is cos alpha 2, I get it as V2 cos alpha 2, or delta V is what? It is V1 plus V2 becomes V1 cos alpha 1 plus V2 cos alpha 2. And this V2 cos alpha 2 already we have discussed in the previous sessions also. I can write in terms of cos beta 2, that it becomes VR2 cos beta 2 minus U. We have discussed already in the previous sessions. The same I am applying here using the cosine functions. So now I am replacing the value of V2 cos alpha 2 is VR2 cos beta 2 minus U in this particular equation. It becomes in this particular form. Now, already we know that for the reaction turbine at the starting only, we have discussed that the value of VR2 is equal to V1, which means I will replace this value of V1 here. Similarly, the value of beta 2 as alpha 1 as here. So we are remaining with delta V is equal to V1 cos alpha 1 plus V1 cos alpha minus U, or it becomes 2V1 cos alpha 1 minus U. This is our equation number 2. Then we substitute this one in our work done equation, that is the equation number 1, and we get it in this form. Do the simplification, you get it as 2uv1 cos alpha 1 minus u square. Students, when we are finding the blade efficiency, always keep in mind you should get the equation in that form of the ratio, speed ratio, that is u by v1. So now if you observe here we are having the terms uv1, you are having the terms here u square. I want to get in the form of the speed ratio, that is u by v1. So what I can do is, for this particular equation, I will divide it by v1 square as well, sorry, multiply by v1 square and divide by v1 square. So which means I am not doing any change to this particular equation. So once I do this form, you can see here this becomes one term u square by v1 square, and another term it is taken to the next side. So multiplying and dividing by v1 square, you can see here I can write it as in this form, that is v1 square into 2u v1 cos alpha 1 minus u square by v square. In terms of pi, I get the equation now, that is this one u by v1 becomes pi here. Similarly, u square by v1 square becomes pi square here. So therefore, speed ratio, I get it as v1 square by gc into 2 pi cos alpha 1 minus pi square. This is equation number 3. This is the W. Similarly, I need to go for finding the kinetic energy to the fixed blade, that is v1 square by 2gc with respect to the moving blades, that is vr2 square minus vr1 square by 2gc. So in the reaction turbines, we know the total enthalpy, it is nothing but we take the sum of both moving blades and fixed blades together. So I can write it as v1 square by 2gc plus vr2 square minus vr1 square 2gc. Now what I will do is, in this particular relation, I will split these terms individually to get the form in this form, that is v1 square by 2gc plus vr2 square by 2gc minus vr1 square. Students, already I have discussed that here the value of vr2 square, that is the value of vr2 something, but it is equal to v1. So if I substitute, this becomes v1 square by 2gc, and therefore it becomes in this form v1 square plus v1 square by 2gc, it is 2 v1 square by 2gc. 2 gets cancelled, we get this as v1 square by gc minus vr1 square 2gc. Or using the inlet velocity triangle, what I will do is I will find the value of vr1 square using this cosine rule for this particular triangle, students, that is DAB. That is vr1 square is equal to the sum, the square and sum and square of the other two sides, that is u square plus v1 square minus 2u v1 into cos alpha 1. I'll substitute this particular value in this particular equation here. So on substitution, what do I get here, students? I get it as v1 square minus gc minus v1 square plus u square minus 2 v1 u1 cos alpha 1 by 2gc, or on simplification it gets in this particular form. So now you can see here again we are getting in the form of u square u. So again, what I want to get? I want to get in the form of the speed ratio pi itself. So again, I will do here small manipulations such that I can get in the form of speed ratio. So what I am doing is I am taking v1 square by 2gc as common. So I get it as 1 plus 2u by v1 cos alpha 1 minus u square by v1 square, which means the replacement for speed ratio pi. Similarly for pi square, here I get. So it becomes v1 square by 2gc 1 plus 2 pi cos alpha 1 minus pi square. So therefore now the blade efficiency is what? It is work input, work divided by the velocity input, that is I can see here W by delta H naught. So therefore the blade efficiency Now I can term it as in this form. That is W by delta H naught, or putting the values of W and delta H into form of the speed ratios, that is pi square, you can see here. So if you make the simplifications, you can see this term gets cancelled, this gets cancelled, the 2 value it moves to the numerator, it becomes 2 pi cos alpha 1 minus pi square. Students, one more important thing here, the term which you are observing here in the denominator, it is what? 1 plus 2 pi cos alpha 1 minus pi square. In the numerator it is almost there, but only 1 is missing. So what I will do is, within the bracket, inside this bracket, I will add 1, I will subtract 1, plus 1 minus 1, no change, which means I will get in the denominator form. So it becomes in this form. Then this minus 1, I will take it out of the bracket and it forms this particular thing, that is minus 2. Now you can see here we are getting the same form. Why? It becomes easy for simplification. That is, in this particular form, the simplification it is happening here. Eta b is equal to 2 minus 1 plus 2 pi cos alpha 1 minus pi square. That is moving towards one part. Or the maximum blade efficiency, now I can take it as dou eta b by dou pi is equal to 0, where on doing the simplification, we get it as 2 cos alpha 1 minus 2 pi is equal to 0, or cos alpha 1 is equal to pi. If you observe here, students, what is pi? This pi is nothing but it is equal to u by v1, that is speed ratio. Now, these are all together taken as a single form, that is, for reaction turbine, speed ratio is nothing but it is cos alpha 1, you can say. So, therefore, I can write it in this form, or the maximum blade efficiency, wherever pi is there, a substitute value as cos alpha 1, it gets the form in this form, that is 2 minus 2 divided by 1 plus cos square alpha 1, which means on simplification, you can see this term gets cancelled and it's remaining with the blade efficiency, maximum blade efficiency as 2 cos square alpha 1 divided by 1 plus cos square alpha 1. Hope this is clear to you all, students. This is the equation. This is the equation for maximum blade efficiency for an reaction turbine. Now, one more concept is left regarding the discussion of the effect of reheat factor and stage efficiency. Sometimes in the turbines, the steam expansion takes place in a number of stages. So we call it as to find out the stage efficiency. Now, if you observe here, we have drawn a Moliere chart and you have shown some pressure lines. There is pressure line P1, pressure line P2, P3, P4, P5. Here the steam expansion happens to occur in 4 number of stages. So this is the stage 1, stage 2, stage 3, as well as stage 4. So as the steam expands in 4 number of stages between the 5 pressure lines, you can see here, if the actual isentropic expansion begins to happen, it has to happen from 1 to 5, 1 to 5 dash. That is the isentropic expansion. But due to the losses, we get the actual expansion which begins from here, that is 1 to move towards 5. So this is a large process. So if we make it in a small number of stages, we get in the form of the stage efficiencies for each number of stage. So totally now we have considered here 4 stages. We are having 5 pressure lines. So 4 stages, you can find out each stage efficiency for each turbine. Suppose for first stage, I can find out eta S1. Similarly, for a second stage, I can find out eta S2. Then similarly for the third stage, I can find out eta S3. And for the fourth stage, I can find out eta S4. Now I will combine them all this together and I will find out the overall efficiency, the whole together itself, considering the efficiency of all the stages together with the term known as reheat factor. So here particularly you can consider that there is a steam which is expanded from 1 to 5, actual expansion with the isentropic expansion of 1 to 5 dash. Now here the thermodynamic effect on the turbine efficiency, As I said, we're considering with the 4 stages, and the total expansion we are divided into 4 stages having the pressure ratio. Remember that for each stage, that is this stage, and the second stage, that is from 2 to 3 here, then the next stage, that is from 3 to 4 here, and the last stage, that is from here. For each stage, the stage efficiency remains same. Also, the pressure ratio also remains same. The pressure also remains same. It doesn't change. So, for example, for the first stage, I can say that the pressure ratio is P2 by P1. Similarly, P1 by P2. It should be P1 by P2. Sorry, it should be P1 by P2 for the first stage. Second stage, it should be P2 by P3. Like this for other 2 stages we are writing. And this pressure ratio, it remains the same for all the stages along with their stage efficiencies also. So therefore, I get it in the form of pressure ratio. And if I consider eta naught as my overall expansion, overall efficiency of the expansion, then I can define it as the ratio of actual work done per kg of steam. So this is the point. This is the actual work done, students. That is from 1 to 5 what you are observing. This is the ratio of actual work done to the isentropic work done. Isentropic work done. It is the expansion which is happening from 1 to 5 dash. This is the isentropic expansion. So I can write mathematically in this form, students. That is eta naught is equal to h1 minus h5 by h1 minus h5 dash, that is wa by ws. Now actual work done, I can write it as wa is equal to eta naught into ws, where ws is what? It is the work done of all the stages, that is the total number of stages. So I can combine them all together as wa is equal to summation of delta wa, where work done for 1 to 2, 2 to 3, 3 to 4, 4 to 5, all are taken the summation of all the work done for all the 4 stages. Similarly, I can write the stage efficiency for each stage. That is, you can see here the stage efficiency for first stage. It is from here. That is, the actual value is h1 minus h2 divided by the another value, that is h1 minus h2 dash, that is here. So I can write it as this form: stage efficiency for the first stage, h1 minus h2 divided by h1 minus h2 dash. So this is the value of actual work done here. Please observe here, students. This is h1 minus h2 divided by h1 minus h2 dash. Similarly, I can write for the other stages also. So for all the stages together, I write it as summation of eta s1 ws1 plus eta s2 ws2 plus eta s3 ws3. And already in the assumptions we have stated that these all stage efficiencies, they are equal to one another, that is equal, say they are same itself, the same stage efficiency. So therefore you can say that we can write it as in this form, that is overall efficiency into ws is equal to the stage efficiency into summation of the delta work done, that is for all the stages together. Now we can write it in this form. This is the equation number 2. So already we know that we have a slope of constant pressure lines on the HS plane as dou H by dou S for the particular P with which is equal to the temperature T, which means the ratio of summation of the isentropic enthalpy drop for the individual stage to the total isentropic enthalpy drop as a whole together, we call it by term known as reheat factor, where reheat factor represented as RF is equal to, as I said, summation of isentropic enthalpy drop, that is delta WS1 plus delta WS2 plus delta. We take individual together, the summation of them to the total whole of the all together, it is WS, and where it is RF is equal to summation of delta S, summation of delta WS by WS, or this I can write it as in this form: overall efficiency is equal to stage efficiency into reheat factor, where always the reheat factor is always greater than 1 and the overall efficiency is always greater than stage efficiency for the turbines. Some more points are regarding the advantages and disadvantages of reheating, why we need to go for reheating. So generally in the turbines, when you are using a steam, it may be in the form of an two-phase mixture, that is a mixture of water particles may be there in the steam. So if you are having, there may be decrease in the efficiency of the turbine. So when you are using a reheated steam, there are chances that you can see we can have an increased output of the turbine. Then due to this, the problems of erosion and corrosion problems, they are avoided to a much extent, greater extent. Also, when you are using the reheating process, then the thermal efficiency also improves. And due to this, even the final dryness fraction of the steam is a good quality, it is an improved quality. And this results in the increase of the blade and the nozzle efficiencies. But apart from that, there are some disadvantages also. That is, it requires more maintenance. Then the increase in thermal efficiency is not appreciable, because even though you have an increase in thermal efficiency, to achieve this one, we need to have more financial burden. That is, the setup has to become more complex in nature. So these are things with respect to the reaction turbines. So in the next session, students, we'll be discussing some of the problems with related to the reaction turbines. Thank you, students.